December the 16th, 1944, the forests of the Ardennes. Heavy snow blanketed the ground as thousands of German soldiers poured through the fog, launching what would become known as the Battle of the Bulge, Germany's last desperate offensive on the Western Front. At positions around Monschau, Germany, lightly armed American cavalry troopers of the 38th Squadron found themselves directly in the path of the assault. Their commander frantically called for artillery support. Colonel George Axelson of the 406th Artillery Group faced an impossible decision. He had the weapon that could save these men, a new type of artillery shell that had just been issued to his unit. The problem was that Supreme Commander Dwight Eisenhower had not yet authorized its use. The weapon was so secret, so revolutionary, that Pentagon officials feared even a single unexploded shell falling into German hands could compromise one of the most closely guarded technological achievements of the war. Axelson made his choice. The emergency trumped protocol. He ordered his gunners to load the special ammunition. Minutes later, shells began exploding not on impact with the ground, but 30 feet above the heads of the attacking Germans. The assault collapsed. German soldiers who had survived the barrage emerged from cover in what prisoner interviews later described as a dazed state. They had no idea what had just happened to them. They realized they were facing something new, something they couldn't understand and something they couldn't evade. What the Germans had just experienced was the proximity fuse, a 5-pound marvel of American engineering that would transform artillery warfare and help bury the Wehrmacht under an avalanche of precisely detonated airbursts. But this story doesn't begin in the snows of the Ardennes. It begins with a fundamental problem that had plagued artillery since the invention of flight. Hitting an aircraft with an artillery shell is extraordinarily difficult. You're not aiming at where the plane is, you're aiming at where it will be when your shell arrives. By World War II, anti-aircraft gunners had two options, both deeply flawed. Contact fuses required a direct hit on a fast-moving target thousands of feet in the air. The odds of success were astronomical. Time fuses were set to explode at a predetermined altitude based on calculations of the target's height and speed, but these calculations depended on accurate observation and quick mental math performed under combat stress. Get the timing wrong by even a second, and your shell exploded harmlessly in empty sky while enemy bombers flew on untouched. The Germans knew these limitations better than anyone. By 1942, the Luftwaffe had deployed over 15,000 of their famous 88mm flat guns across defensive belts stretching from the Netherlands through Belgium and Western Germany. These weapons, originally designed as anti-aircraft guns in the 1920s, had proven to be among the most versatile and feared artillery pieces of the war. The 8 could fire 15 to 20 rounds per minute, sending 17-pound shells to altitudes exceeding 26,000 feet, where they would explode into 1/500 fragments or more, leaving characteristic black puffs of smoke. Any aircraft within 200 yards faced scything shards of metal. German batteries of 4 guns each, coordinated by the Commando Jarrett 40 fire control system, created walls of exploding steel that Allied bomber crews learned to dread. The problem was efficiency. Despite their fearsome reputation, despite the thousands of guns and millions of shells, German anti-aircraft artillery struggled with a brutal mathematical reality. One Luftwaffe study estimated it took over 3,300 88mm shells to successfully shoot down a single bomber. Think about that number. 3,300 shells, each requiring precise manufacturing, transport and handling for one kill. This wasn't a failure of German engineering or gunnery skill. This was the fundamental limitation of time-fused anti-aircraft fire. You were throwing shells into a predicted point in space and hoping the bomber arrived at exactly that moment. The Americans understood this problem and decided to solve it with technology that seemed impossible. The idea of a proximity fuse, a device that could sense when it was near a target and automatically detonate, had been around since the early 1930s. The Germans had worked on it. The British had worked on it. The Japanese would eventually develop a working version, but deploy it only once, too late to matter. Everyone understood the concept. The execution was where it became impossible. To work in an artillery shell, a proximity fuse needed to survive forces that would destroy any conventional electronics. When an 88mm gun fired, the shell experienced acceleration forces up to 20,000 times the force of gravity. It was then spun by the rifling of the barrel at up to 30,000 revolutions per minute, creating immense centrifugal force. Any device inside that shell had to survive these forces, then function reliably at altitudes where temperatures dropped far below zero, then sense the presence of a target, calculate the optimal detonation distance, and trigger the explosive charge, all in fractions of a second. In the 1930s and early 1940s, electronics meant vacuum tubes, fragile glass components that shattered if you dropped them on a table, let alone subjected them to the violence of artillery fire. The Germans tried. Documents captured after the war revealed they had developed perhaps as many as 50 different proximity fuse designs for anti-aircraft use. These included acoustic fuses triggered by engine sound, an electrostatic design by Rheinmetall Borsig, and various radio-based concepts. Some of these reached testing stages. One German design demonstrated 95% reliability against a metal cable target and could detect objects 10 to 15 meters away. The problem was always the same. The vacuum tubes couldn't survive, being fired from a gun. In 1940, Hitler actually ordered work on proximity fuse halted. German engineers had concluded it was simply impossible to build electronics rugged enough for artillery use. When development restarted in early 1944, Allied forces overran the facilities before production could begin. The Germans never fielded a single working proximity fuse in combat. The British came closer. As early as 1939, British scientists were developing proximity fuse devices for rockets and bombs. Rockets had much lower acceleration and no spin, making them far easier platforms for delicate electronics. The British focused on photoelectric fuse using light-sensitive receptors to detect targets. These worked reasonably well in the larger warheads of anti-aircraft rockets, and several inventors had filed patents on various designs. But rockets lack the range and accuracy of artillery. The British effort was part of what Prime Minister Winston Churchill called the Wizard War, the secret technological struggle underlying the visible conflict. British researchers made real progress, but they ran into two insurmountable obstacles. The costs spiraled out of control, and British industry simply couldn't manufacture the miniaturized components in the quantities needed. It took American industrial capacity and American scientific persistence to turn the impossible into reality. In June 1940, as France fell and Britain stood alone, President Roosevelt created the National Defense Research Council to coordinate military research. Among its first priorities was improving anti-aircraft defenses. The threat was obvious. Japanese forces were expanding across the Pacific, and their aircraft threatened American ships. German U-boats were sinking ships faster than they could be replaced. The war in Europe demonstrated that air power would be decisive, and whoever could defend against aircraft most effectively would have an enormous advantage. Representatives from the Navy and the NDRC met to discuss recent developments. Information from British work on proximity fuses for bombs and rockets led to a crucial question. Could such a device be adapted for ship-based anti-aircraft guns? The Navy was particularly interested. In the vast expanse of the Pacific, ships operated far from land-based air cover. A kamikaze attack, a determined dive bomber, could sink a carrier or cruiser before conventional anti-aircraft fire could stop it. The discussion led to the creation of Section T at the Johns Hopkins University Applied Physics Laboratory, headed by physicist Merle Tuve. Tuve was brilliant, short-tempered, and absolutely determined to solve the proximity fuse problem. By the end of the project, Section T would grow to over 1,000 scientists, engineers, and support staff. An estimated 3% of all physicists in the United States worked on the proximity fuse at some point. The challenge they faced was staggering. They needed to build what was essentially a miniature radar system complete with transmitter, receiver, power source, and triggering circuit, small enough to fit inside an artillery shell, rugged enough to survive being fired, and cheap enough to be manufactured by the millions. The solution required breakthrough after breakthrough. First, the tubes. Working with Western Electric and Raytheon, the team modified miniature vacuum tubes originally designed for hearing aids. These were the smallest, most rugged tubes available, but they still had to be extensively redesigned. The glass envelopes were strengthened, the internal elements were reinforced, every component was tested to destruction and rebuilt stronger. By January 1942, the T3 fuse achieved a 52% success rate against water targets. The Navy accepted that failure rate. In combat, a weapon that worked half the time was infinitely better than existing systems. but Section T kept refining the design. The principle was elegant. The fuse contained a tiny radio transmitter that used the shell's metal body as an antenna, broadcasting a continuous wave at roughly 180 to 220 MHz. As the shell approached a target, the radio waves reflected back, and a receiver detected these returns. The key innovation came from Lloyd Berkner, who developed separate transmitter and receiver circuits, and from scientists at the National Bureau of Standards who applied the Doppler effect. As the shell moved toward a target, the frequency of reflected radio waves shifted, and this shift could be detected and measured. When the fuse sensed it was close enough to a target, typically within 70 feet, it triggered the detonation. The shell exploded while still in the air, creating a lethal sphere of shrapnel that didn't require a direct hit to destroy an aircraft. But even with working electronics, enormous challenges remained. The fuse needed a power source. Batteries in 1942 were heavy, unreliable, and had limited shelf life, especially in the tropical conditions where the Navy would first use these weapons. Engineers developed special reserve batteries that activated only when the shell was fired. The centrifugal force from the shell's spin drove a generator that powered the electronics. Everything had to be miniaturized. The complete fuse contained about 130 individual electronic components, each manufactured to tolerances of thousandths of an inch, and everything had to be assembled by hand. By late 1942, production facilities were established. Sylvania Electric Products in Ipswich, Massachusetts became the largest production site, eventually producing over 5.6 million fuse, more than any other location. The work was done primarily by women, assembling the delicate parts by hand hundreds at a time in tedious work that strained the eyes. These women didn't know what they were building. Security was absolute. They were searched entering and leaving the plant. They couldn't bring purses inside. Even the Ipswich Police and Fire Department were prohibited from entering the building. By war's end, over 22 million proximity fuse would be produced by more than 100 manufacturers across America. Secrecy surrounding the fuse rivaled the Manhattan Project. The device was given the deceptive designation VT fuse, supposedly standing for variable time to hide its true nature. Anyone who saw an unexploded VT fuse would assume it was just another type of time fuse. The real designation was proximity fuse, but that name was never used in official communications. Military planners obsessed over the possibility of a dud falling into enemy hands. If the Germans or Japanese captured an intact fuse and reverse-engineered it, they could potentially develop their own versions or, worse, create jamming systems to defeat it. This fear drove strict protocols on where the fuse could be used. Initially, VT fuse were only authorized for use over water, where dud shells would sink beyond enemy recovery. This limited the fuse to naval anti-aircraft use in the Pacific, where the Japanese Navy operated far from land, and duds would fall into deep ocean. In November 1942, the Navy sent 5,000 of the new fuses to Pearl Harbor. Deke Parsons, a naval ordnance officer who had been instrumental in the VT fuse project and would later arm the atomic bomb Little Boy on the way to Hiroshima, personally oversaw their deployment. He consulted Admiral Halsey, who identified the cruiser Helena and the carriers Enterprise and Saratoga as most likely to come under air attack. The fuses were loaded aboard these vessels. On the morning of January 5, 1943, the moment arrived. 4 Japanese Aichi D-3A dive bombers, called VALs by the Allies, surprised a US Navy task force operating off Guadalcanal. Though slow and obsolete, the VAL remained dangerous due to its accuracy and durability. One scored a hit on the attached New Zealand cruiser Achilles before the group began breaking off its attack. Anti-aircraft gunners aboard the cruiser USS Helena unleashed what seemed like a cursory barrage on the departing VALs. Helena's defences included a dozen 5-inch guns plus short-range 20 and 40mm weapons. 2 5-inch salvos were fired. One VAL exploded in mid-air and crashed into the sea. The gunners hadn't directly hit it. Instead, at least one shell had passed close enough to the dive bomber to detonate automatically, fatally damaging the aircraft with a blast of shrapnel. This was the combat debut of the proximity fuse, the first time in history that an artillery shell had automatically detected its target and chosen the optimal moment to explode. The results were immediate and dramatic. Throughout 1943, naval guns fired 36,270 anti-aircraft rounds in the Pacific. Although only 25% used proximity fuses, these accounted for 51% of the kills. The new shells had a lethal fragment area of about 3,000 square feet, compared to 60 square feet for conventional time fuses. Night kill ratios increased by 370%. The startling effectiveness led the Navy to use proximity fuses 75% of the time. Statistics told the story. Conventional time-fused 5-inch shells required an average of 508 rounds to kill one aircraft. Proximity-fused shells needed only 155 rounds per kill. Against determined attacks, the difference meant survival. Consider the suicide attack on May 11, 1945, against destroyers Hadley and Evans during the Battle of Okinawa. The small group of ships and planes faced 156 enemy aircraft in a 90-minute engagement. The Evans was hit 4 times by suicide planes before having to retire. The Hadley knocked down a dozen enemy planes. The Evans accounted for 23 kills before withdrawing from the fight. The verdict on VT-fused ammunition was indispensable. Secretary of the Navy James Forrestal stated that without the protection the proximity fuse gave surface ships, the westward push across the Pacific could not have been so swift, and the cost in men and ships would have been immeasurably greater. Pacific Theater Commander Admiral Nimitz estimated that the proximity fuse had increased the effectiveness of anti-aircraft fire by a factor of 3 to 4. The fuse helped blaze the trail to Japan. But while the Navy was revolutionizing naval air defense in the Pacific, the proximity fuse remained locked away from its most potentially devastating application: ground-based artillery against enemy troops. Pentagon officials remained adamant. The risk of capture was too high. The technology was too valuable to risk over land where German or Japanese forces might recover a dud shell. Then, in June 1944, everything changed. After D-Day, as Allied forces pushed into France, the Germans unleashed their vengeance weapons against London. The V-1, a jet-powered cruise missile called the Buzz Bomb by Londoners, began raining down on the British capital. Flying low and fast at about 400 miles per hour, V-1s were extraordinarily difficult targets. RAF fighters could intercept some. Anti-aircraft guns positioned along the coast got others. But the success rate was abysmal. In early June 1944, only 17% of V-1s approaching through the coastal gun belt were destroyed. Each one that got through carried a 1,270-pound warhead into London's residential neighbourhoods. The city was being systematically destroyed. Winston Churchill personally intervened and demanded the Americans release the proximity fuse for use against the V-1s. On June 12, 1944, the United States authorized the use of proximity fuse overland for the first time, specifically for defense of London against German V-1 attacks. The transformation was immediate and spectacular. British anti-aircraft batteries equipped with American proximity fuse and improved fire control radar saw their success rate skyrocket. From the first day of attacks to the end of August, the Germans launched 9,300 V-1s, an average of 120 per day. By the end of the 4th week, anti-aircraft shells equipped with proximity fuses accounted for the destruction of 79% of all incoming V-1s. During one day, the success rate reached 82%. Over the course of the V-1 campaign, the proportion of flying bombs destroyed while flying through the coastal gun belt rose from 17% to 74%. The proximity fuse had saved London. As one Section T scientist recorded in a letter, you can be sure that the VT fuse has saved the lives of thousands here. One interesting problem emerged. The fuse proved so sensitive that it would detonate if a shell passed too close to a seabird. British records noted a number of seabird kills by proximity-fused shells. When the British 11th Armoured Division captured Antwerp in September 1944, the vital port immediately came under attack from V-1 flying bombs. The Germans launched round-the-clock attacks, firing some 1,200 V-1s and V-2 ballistic missiles over the next 5 months, attempting to destroy the port. When the Germans modified V-1s to fly as low as 2,200 feet, making interception vastly more difficult, physicists at Applied Physics Laboratory quickly designed a modified fuse for 3.7 and 90mm anti-aircraft shells to counter the low-altitude threat. The devices were rushed into production at the Crosley factory in Cincinnati, Ohio. Churchill authorized a special flight of Lancaster bombers to transport the fuses from Cincinnati to Antwerp. Once employed, A single anti-aircraft battalion destroyed 48 of the first 75 V1s they encountered. With the aerial attacks largely thwarted, the Great Supply Port remained open without interruption for the duration of the war. By the end of the war, proximity-fused anti-aircraft defences around Antwerp had accounted for more than 2,000 V1 kills. The success over England and Antwerp finally convinced military planners that the proximity fuse's time had come for its ultimate application. Field artillery against ground troops. Large supplies of fuse for all calibers of US artillery had already been shipped to Europe with the army code name POSIT. They sat in ammunition dumps waiting for authorization. General Eisenhower and his staff understood the weapon's potential, but the embargo remained in place until December 16, 1944. When German armour broke through the Ardennes forest to launch the Battle of the Bulge, Eisenhower immediately demanded authorization to use the proximity fuse. The emergency was obvious. German forces were advancing rapidly. American units were surrounded or in danger of being overrun. Conventional artillery wasn't stopping them. 3 days after Colonel Axelson broke the embargo at Monschau, Eisenhower formally requested clearance. 2 days later, on December 21st, all restrictions were removed. The effect on the Germans was swift and devastating. Proximity fuse were set for airburst detonations 30 to 50 feet above ground. When shells exploded at this height, they created a lethal cone of shrapnel spreading downward and outward. Foxholes provided no protection. Trenches became death traps. The fragments even penetrated log-reinforced revetments that had protected against conventional artillery. German soldiers caught in the open had nowhere to hide. Traditional artillery required observers to see the target and calculate the proper time fuse setting. Bad weather, fog or darkness made accurate time fuse settings impossible, but proximity fuses didn't require observation. As long as artillery could calculate the general target area, the fuses would automatically detonate at the optimal height above whatever was there. For the Germans attacking through the Ardennes in December, often moving under cover of fog and snow, this was catastrophic. As the artillery was high velocity, targeted German soldiers often couldn't hear the shells until they burst overhead. Prisoner of war interviews repeatedly described the psychological impact. German soldiers emerged from barrages in what interrogators termed a dazed state. They realized they were facing a new type of artillery, but could understand neither how it worked nor how to evade it. One German prisoner described the attacks as quick, powerful bursts for which there was simply no defense. The demoralizing effect was particularly severe at night when soldiers couldn't see the airburst coming. The effectiveness caused what American intelligence reports described as near mutiny in some German units. Soldiers began refusing orders to move out of bunkers during an artillery attack. Officers who insisted on maintaining offensive operations faced troops who simply wouldn't advance into areas where the mysterious airbursts were landing. General George Patton witnessed the effects firsthand. His Third Army was driving north to relieve Bastogne when his artillery units began employing the new fuse. On the night of December the 25th and 26th, 1944, American artillery caught a German battalion attempting to cross the Sauer River near Echternach. Patton reported that by actual count, 702 German soldiers were killed. The concentrated firepower of a battalion of American guns firing proximity-fused shells had simply annihilated an entire German unit in minutes. Patton wrote to Major General Levin Campbell, the Chief of Army Ordnance, describing the devastating effects. "The new shell with the funny fuse is devastating," Patton wrote. "We caught a German battalion which was trying to get across the Sauer River with a battalion concentration and killed by actual count 702. I think that when all armies get this shell, we will have to devise some new method of warfare. I am glad that you all thought of it first." Later, Patton would famously claim that the funny fuse won the Battle of the Bulge for us. While historians note that only limited use was made of the fuse before January due to logistical constraints, its psychological impact on German forces was disproportionate to the number of shells fired. German commanders quickly realized they were facing something unprecedented and issued orders offering rewards for any soldier who could recover an intact fuse. They desperately needed to understand how the weapon worked and whether countermeasures were possible, and here the story takes an almost unbelievable turn. During the Battle of the Bulge, German forces captured an American ammunition dump containing approximately 20,000 proximity fuses for artillery shells. Think about that. The Germans had in their possession thousands of examples of the weapon that was devastating their forces. They had the opportunity to examine the technology, reverse engineer it, potentially develop countermeasures, or even copy it for their own use, but nothing happened. German engineers examined the captured fuses and concluded they were triggered by the Earth's magnetic field. They couldn't conceive that the devices were actually tiny radio transceivers because they had already determined such a thing was impossible. The vacuum tubes couldn't survive being fired from a gun. Since German engineers knew this was impossible, they looked at the captured fuses and literally couldn't see what they were looking at. The German military had concluded years earlier that proximity fuse were an impossible idea that would never be practical. When confronted with physical evidence that the impossible had been achieved, they refused to believe it. The captured fuse was set aside. No serious attempt was made to understand or copy them. The technology that could have changed German artillery effectiveness remained incomprehensible to engineers who had decided it couldn't exist. Meanwhile, back in the United States, Section T scientists learned that Germans had captured 20,000 fuse and immediately feared the worst. Winfield Salisbury had developed a radio jammer specifically designed to defeat the proximity fuse. 200 jammers were quickly constructed and installed in American bombers in England, ready to deploy if Germans started using the captured fuse or developed countermeasures. The jammers were never needed. The Germans never recognized what they had. The proximity fuse's impact extended far beyond the Battle of the Bulge. During the 3 months of the US Army's advance from the Bulge to the crossing of the Rhine, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. On January 1, 1945, the Luftwaffe launched Operation Bodenplatte, a desperate attempt to destroy Allied air power by attacking airfields across Belgium and the Netherlands. Nearly 900 German fighters participated in surprise attacks against Allied airfields. At several locations, the attacks initially succeeded, destroying aircraft on the ground. But German losses were catastrophic. The Luftwaffe lost 277 planes during Bodenplatte. While 62 were shot down by Allied fighters, 172 fell to anti-aircraft fire, much of it using proximity fuses. The Germans had expected to face the usual anti-aircraft defences protecting airfields. Instead, they flew into walls of precisely detonating airbursts. Proximity-fused anti-aircraft shells had been deployed to defend against V-1 attacks and were positioned around Allied airfields in unprecedented numbers. The loss of 172 aircraft to flak in a single day, many shot down by the very proximity fuses the Germans didn't understand, was a disaster the Luftwaffe could not recover from. These weren't just aircraft losses, these were experienced pilots, many of them instructors, squadron leaders, and veterans. The training system was already collapsing under Allied bombing. Losing 213 pilots in one day, including irreplaceable leaders, was a blow from which the Luftwaffe never recovered. Operation Bodenplatte effectively ended the Luftwaffe as a fighting force. For the rest of the war, German air activity was sporadic and ineffective. Proximity-fused anti-aircraft fire had played a crucial role in achieving Allied air supremacy. In northern Italy, the proximity fuse demonstrated another capability. On April 1945, B-24 Liberator bombers began dropping VT-fused bombs on German anti-aircraft gun emplacements. The effect was immediate and devastating. German flak batteries that had been protecting targets for months were suddenly silenced. The bombers dropped their airburst weapons over the gun positions, and the anti-aircraft batteries simply ceased to exist. Crews were killed, guns were damaged, and fire control systems were destroyed. This allowed the main body of bombers to fly through previously defended corridors without molestation. One of the first American uses of proximity fuses on unrotated bombs was against gun positions on Iwo Jima prior to the February 1945 landings. The Marines would still face horrific opposition on Iwo Jima, but the preliminary bombardment using airburst bombs had neutralized more defensive positions than conventional munitions could have. The mathematics of the proximity fuse's effectiveness was staggering. In the Pacific, one Section T developer estimated that 278 planes were destroyed by proximity-fused ammunition, while conventional time fuse would have accounted for only 46. A Navy study found that for every enemy plane destroyed, 5-inch guns firing time-fused shells had to fire 1,000 rounds, while proximity-fused shells required only about 250 shots. That's a 4-fold increase in effectiveness. Apply that across thousands of engagements and millions of shells, and you begin to understand why Secretary of Defense James Forrestal and Admiral Nimitz credited the proximity fuse with making the Pacific advance possible. The fuse's impact on land warfare was equally revolutionary. Artillery that had been a weapon of area suppression became a weapon of precise destruction. Commanders could target enemy formations with confidence that their shells would detonate at the optimal height to maximize casualties. The effect on enemy morale was devastating. German and Japanese soldiers learned that there was no protection from proximity-fused artillery. You couldn't hide in a foxhole. You couldn't shelter in a trench. Log-covered bunkers that stopped conventional shells were penetrated by the downward spray of fragments from airbursts. By war's end, statistics revealed the proximity fuse's impact. Just over 22 million VT fuses were produced during World War II by more than 100 manufacturers. The program cost over $1 billion in 1940s dollars, roughly $15 billion in today's money. Each fuse contained about 130 miniaturized electronic parts and cost approximately $18 to produce in 1945, equivalent to about $314 today. This was expensive, but not prohibitively so. A 155mm artillery shell cost significantly more than the fuse it carried. For a weapon that tripled or quadrupled artillery effectiveness, the cost was negligible. General Eisenhower gave immense credit to the proximity fuse. In his post-war assessment, he stated that it seemed likely that if the Germans had succeeded in perfecting and using these new weapons 6 months earlier than they did, the invasion of Europe would have proven exceedingly difficult, perhaps impossible. This is an extraordinary statement. Eisenhower believed that if the Germans had developed their V-weapons earlier, they might have prevented D-Day. But the proximity fuse had neutralized the V-1 threat and dramatically increased the effectiveness of Allied artillery and anti-aircraft defenses. Vannevar Bush, head of the US Office of Scientific Research and Development during the war, credited the proximity fuse with 3 significant effects. First, it was crucial in defense against Japanese kamikaze attacks in the Pacific. Bush estimated a 7-fold increase in the effectiveness of 5-inch anti-aircraft artillery. Second, it was essential to the radar-controlled anti-aircraft batteries that finally neutralized German V-1 attacks on England. Third, it was used in Europe starting with the Battle of the Bulge, where it proved very effective against German infantry formations and changed the tactics of land warfare. Bush's assessment was that while no one invention won the war, the proximity fuse must be listed among the very small group of developments, such as radar, upon which victory very largely depended. The German failure to develop the proximity fuse, despite working on the concept since the early 1930s, despite capturing 20,000 examples during the Battle of the Bulge, stands as one of the war's great technological failures. It wasn't for lack of trying. German scientists and engineers were brilliant. They had developed jet aircraft, ballistic missiles, and numerous other advanced weapons. But they had convinced themselves the proximity fuse was impossible, and that conviction blinded them to evidence that it had been achieved. When German anti-aircraft batteries defending the Reich needed 3,388mm shells to kill one bomber, they were fighting with World War I technology. Time fuses that required perfect calculation and observation. Contact fuses that required impossible accuracy. Meanwhile, American ships in the Pacific were shooting down aircraft with 1/4 the ammunition expenditure. The difference wasn't German incompetence, it was American industrial capacity married to scientific innovation. The proximity fuse represented everything the United States did well in World War II, identifying a crucial problem, assembling the best scientific minds to solve it, developing manufacturing processes to produce the solution in vast quantities, and maintaining absolute secrecy until the weapon could be deployed in overwhelming numbers. The program involved more than 100 factories, thousands of workers, many of them women with no previous industrial experience, scores of physicists and engineers, all working on a device so secret that most participants didn't know what they were building. And when the weapon finally appeared on the battlefield, it changed warfare. German artillery crews who had mocked the idea of an automatic fuse found themselves facing artillery that exploded with perfect timing above their heads. Luftwaffe pilots who had survived years of combat against conventional anti-aircraft fire were blown from the sky by shells that didn't need to hit them directly. Japanese kamikaze pilots who relied on speed and surprise to penetrate anti-aircraft defenses found American ships surrounded by walls of precisely timed explosions. The psychological impact was as important as the physical destruction. When you face a weapon, you don't understand. When traditional cover provides no protection, when tactics that worked yesterday are useless today, morale collapses. German prisoner interviews repeatedly emphasized the demoralizing effect of proximity-fused artillery. The quick, powerful bursts for which there was simply no defense, the way shells exploded overhead without warning, the inability to find shelter. Several German units experienced what intelligence reports described as near mutiny, with soldiers refusing to advance into areas where the airbursts were falling. This wasn't cowardice. These were often veteran units that had faced conventional artillery for years, but proximity-fused artillery was different. It was personal. It found you wherever you hid. And the Germans couldn't understand how it worked, which made it even more terrifying. After the war, captured German documents revealed the extent of their proximity-fuse development efforts. They had tried acoustic fuses triggered by engine sounds, electroacoustic fuses developed by the Graf Zeppelin Institute, radio fuses by AEG Berlin intended for the HS-117 and HS-298 missiles, electromagnetic fuses by the Orlich Institute of Danzig, the Kakadu radio fuse by Donau Landische GmbH of Vienna, of which 3,000 were actually produced for the HS-293, the Kranich acoustic fuse by Ruhrstahl AG, which was highly rated, the Kugelblitz radio fuse and numerous others. None of these ever saw service in artillery. Some were tested in missiles and rockets where the lower acceleration forces made survival easier. But for the crucial application, anti-aircraft guns defending German cities and field artillery supporting German armies, the proximity fuse remained impossible until it was too late. The legacy of the World War II proximity fuse extends far beyond 1945. Today the principle is used in major weapon systems around the world. The Phoenix AIM-54 air-to-air missile, the Standard Missile SM-1 and SM-2 surface-to-air missiles, the Patriot surface-to-air missile that proved effective during the Gulf War. Modern artillery shells come with a variety of fuse options, including sophisticated proximity fuses that can be programmed for specific detonation parameters. The technology has evolved from fragile vacuum tubes to solid-state electronics to microprocessors, but the principle remains the same. Sense the target, calculate the optimal detonation point and explode. The technological breakthrough in World War II was proving this could be done in the brutal environment of artillery fire. Once that barrier was broken, everything else became engineering refinement. In December 1944, when German soldiers emerged from the first proximity-fused artillery barrages in a dazed state, unable to understand what had happened to them, they were experiencing the future of warfare, artillery that didn't require perfect aim, weapons that adapted to their targets, smart munitions that made decisions about when to explode. The proximity fuse was the world's first smart weapon, and it changed everything. German artillery crews had mocked the idea when they first heard rumours of it. Automatic fuses that detected targets? Impossible. Radio transmitters small enough to fit in a shell? Impossible. Electronics that could survive being fired from a gun? Impossible. Until December 16th, 1944, when the impossible started exploding above their heads and their guns fell silent, not because they were destroyed, but because proximity-fused counter-battery fire was systematically eliminating German artillery positions with unprecedented accuracy. The crews who survived understood that they were facing a weapon they had no answer for, a weapon their own engineers had declared impossible, a weapon that helped bury the Wehrmacht under an avalanche of precisely timed airbursts. The funny fuse, as Patton called it, was one of the decisive weapons of World War II, and the Germans never saw it coming. The development of countermeasures became a German obsession in the final months of the war, but it was already far too late. When German scientists finally understood they were facing radio-based proximity fuses, they attempted to develop jamming systems. Documents captured after the war revealed at least 3 separate German programs to create electronic countermeasures. The first approach involved creating portable radio transmitters that would trigger premature detonation of proximity-fused shells. The theory was sound. If you could broadcast signals on the same frequency the fuses used, you might cause them to detonate harmlessly in the air before reaching their targets. German engineers at Telefunken developed several prototype jammers in early 1945. The problem was identifying the correct frequency. The Americans had chosen their operating frequency carefully, using a range that required specialized equipment to detect and jam. German radio intelligence units tried to capture the signal from unexploded shells, but the fuses only activated when fired, and by then they were traveling at supersonic speeds toward their targets. The few fuses recovered intact from duds had their batteries depleted, rendering them inoperative for testing. The second approach was even more desperate. Some German units attempted to create false targets that would trigger premature detonation. They erected metal frameworks and wire arrays designed to present a radar signature similar to massed troops or vehicles. The idea was that proximity-fused shells would detonate when passing these decoys, wasting ammunition and revealing artillery positions. In practice, this failed completely. The Americans had such overwhelming ammunition supplies that wasting a few shells on decoys was meaningless. And the decoys themselves became excellent aiming points for American artillery observers who simply called in more fire on the obvious defensive positions. The third approach was the most practical but also the most telling of Germany's desperate situation. Some commanders ordered their troops to disperse as widely as possible during American artillery barrages. If soldiers spread out with 10 or 15 meters between each man, the reasoning went. Each proximity-fused airburst would only catch 1 or 2 men in its fragment pattern instead of entire squads. This tactic did reduce casualties per shell, but it also rendered German units' combat ineffective. You cannot conduct offensive operations with your forces scattered across hundreds of meters of terrain. You cannot maintain unit cohesion or command and control. The tactic that best defended against proximity fuses was the tactic that guaranteed you couldn't fight effectively. By February 1945, American artillery doctrine had fundamentally changed. Where conventional artillery required careful observation and time-consuming fuse calculations, proximity-fused ammunition simplified everything. Fire missions that once took minutes to set up could be executed in seconds. Artillery-forward observers no longer needed to estimate target altitude or calculate time settings. They simply called in the coordinates and let the fuses handle the rest. The U.S. Army Field Artillery School at Fort Sill, Oklahoma, completely rewrote its training manuals. New graduates arrived in Europe already trained in proximity-fused tactics. They understood that the weapon fundamentally altered the mathematics of artillery effectiveness. A single battery firing proximity-fused shells could cover an area that previously required an entire battalion. Commanders who understood this could achieve the same level of fire support with far fewer guns, freeing up artillery units for other missions. The Ninth Army, pushing across the Roa River in February 1945, employed proximity fuses as their primary anti-personnel ammunition. German defenders, many of them teenage conscripts with minimal training and low morale, broke and ran when the airburst began. Prisoner interrogations revealed that new German soldiers, who had never experienced conventional artillery barrages, were completely unprepared for weapons that exploded overhead without warning. Even experienced soldiers found proximity-fused fire more demoralizing than conventional barrages. One Wehrmacht officer, captured during the Rhine crossing in March 1945, told his interrogators that conventional artillery gave you a chance. You could hear the shells coming, take cover, hope they landed away from your position. But the American airbursts were inescapable. They found you wherever you hid, and the psychological knowledge that cover was useless broke men faster than the actual casualties. This officer estimated that proximity-fused fire reduced his unit's combat effectiveness by 50% before a single man was wounded purely through psychological impact. The statistical evidence supported his assessment. American after-action reports from the final months of the war showed that German units facing proximity-fused artillery surrendered faster, broke more easily, and showed higher rates of desertion than units facing conventional fire. The weapon's effectiveness against aircraft remained equally impressive through war's end. During the Rhine crossings in March 1945, the Luftwaffe made one final attempt to disrupt Allied operations. German jet fighters and conventional aircraft attacked bridges and crossing points, hoping to slow the advance. American anti-aircraft batteries, now equipped almost exclusively with proximity-fused ammunition, created an impenetrable defensive umbrella. Records from the 784th Anti-Aircraft Artillery Battalion show they expended 3,200 rounds of proximity-fused ammunition during the Rhine crossing operations. They claimed 47 aircraft destroyed with an additional 23 probables. Even accounting for the inevitable overclaiming in combat reports, the kill ratio was extraordinary. Less than 70 rounds per confirmed kill, compared to the 3,300 rounds per kill that German 80mm batteries had required earlier in the war. The last major German air operation of the European war came on April 7, 1945, when 183 Luftwaffe aircraft attempted to destroy the Remagen Bridge across the Rhine. American anti-aircraft defences, heavily reinforced after the bridge's capture, included dozens of batteries equipped with proximity fuses. The German attack failed completely. Over 30 aircraft were shot down, most by anti-aircraft fire, and the bridge remained operational until it collapsed from structural damage days later, long after its strategic value had been achieved. German pilots who survived the attack reported flying through what they described as solid walls of exploding shells. One pilot, interviewed after his capture, stated he had never seen such concentrated and accurate anti-aircraft fire. He described shells exploding in precise patterns that seemed to anticipate his evasive maneuvers. He couldn't understand how American gunners could be so accurate. He didn't realize the shells were finding him automatically. In the Pacific Theater, the proximity fuse's impact reached its peak during the Okinawa campaign. The Japanese, desperate to stop the American advance, launched mass kamikaze attacks involving hundreds of aircraft. These suicide planes were the ultimate test of anti-aircraft defences. The pilots were committed to hitting their targets regardless of damage. You had to destroy the aircraft completely to stop it. Proximity fuses proved devastatingly effective against kamikazes. The automatic airbursts caught the attacking aircraft in lethal fragment patterns that shredded engines, control surfaces, and pilots. Even aircraft that weren't immediately destroyed often suffered enough damage that they crashed before reaching their targets. During the 10 major kamikaze attacks at Okinawa between April 6 and June 22, 1945, the Japanese sent nearly 1,500 aircraft against the American fleet. US ships fired millions of rounds of anti-aircraft ammunition, much of it proximity fused. Navy records indicate that approximately 930 Japanese aircraft were destroyed before reaching their targets. Of these, proximity fused 5-inch shells accounted for the majority of kills at medium and long range. The combat air patrol fighters got many at extreme range, and short-range 40mm and 20mm guns caught some at close range. But the 5-inch proximity-fused batteries formed the critical middle layer of defense. Without these weapons, the kamikaze attacks would have been far more devastating. Some ships were still hit and sunk. The destroyer Luce was sunk by kamikazes on May 4th despite her proximity-fused defenses. But the overall survival rate of American ships at Okinawa was remarkable given the intensity of the attacks. Of the 368 ships and craft damaged during the Okinawa campaign, most remained operational or were quickly repaired. The proximity fuse had kept losses from becoming catastrophic. One particularly revealing engagement occurred on May 11, 1945, involving the destroyers Hugh, W, Hadley and Evans, previously mentioned. The small group faced 156 enemy aircraft in a 90-minute engagement. The ships expended their entire supply of proximity-fused ammunition, then switched to time-fused and then contact-fused shells as supplies ran low. The kill rate dropped dramatically with each type of ammunition. While proximity fuses were available, the ships were destroying multiple aircraft per minute. When they switched to time fuses, the rate dropped by more than half. When forced to use contact fuses requiring direct hits, they could barely keep the attackers at bay. Both ships survived but were heavily damaged. More importantly, they had destroyed or damaged so many Japanese aircraft that the attack on the main fleet was significantly weakened. The Japanese did eventually develop their own proximity fuse, but far too late to matter. In early 1945, Japanese engineers completed development of the Type 3 fuse for use in anti-aircraft shells. The device used a photoelectric cell that detected the shadow of an approaching aircraft against the sky. When the shadow reached a certain size, indicating the aircraft was within lethal range, the fuse triggered detonation. The system was ingenious but had severe limitations. It only worked during daylight. It required clear skies. It could be fooled by clouds or smoke. And most critically, it required the aircraft to be approaching from above, passing between the shell and the bright sky. Despite these limitations, the Type 3 fuse worked. It was used operationally exactly once, on the night of August 14, 1945, against American B-29 bombers attacking Tokyo. The attack occurred in the final hours before Japan's surrender, and it's unclear if any B-29s were actually shot down by the new fuse. By the time the Japanese had developed a working proximity fuse, the war was over. The Germans never got that far. Their captured documents show they were still pursuing development in April 1945, even as Soviet armies surrounded Berlin. But they never solved the fundamental problem of building vacuum tubes that could survive artillery forces. The Americans had invested the equivalent of $15 billion in today's money and mobilized thousands of scientists, engineers, and workers. Germany, fighting a losing war on multiple fronts with bombed-out factories and disrupted supply lines, simply couldn't match that investment. Even if they had, they would have needed years to develop manufacturing capability. The war ended before they could even understand what they were trying to build. There's a bitter irony in the German failure. German industry had pioneered miniaturization of electronic components. German scientists were world leaders in radio technology. German engineers had achieved remarkable innovations in numerous fields throughout the war. But they had decided the proximity fuse was impossible, and that institutional decision blinded them to the solution even when it was literally handed to them by the thousands. The post-war interrogations of German scientists and engineers revealed a consistent pattern. When shown actual proximity fuse and told how they worked, the initial reaction was disbelief. That's impossible, they would say. The tubes can't survive those forces. When shown that the tubes demonstrably had survived, they examined the fuses in detail and realized the Americans had solved problems the Germans had considered unsolvable. The reaction then shifted to respect mixed with dismay. If we had known this was possible, they would say, we would have pursued it more aggressively. But the fundamental problem remained that knowing something is possible and having the industrial capacity to build it are two different things. By 1945, German industry was shattered. Factories were bombed. Supply chains were disrupted. Skilled workers were dead or in the army. Raw materials were scarce. Even if German engineers had fully understood American proximity fuses in 1944, they lacked the capacity to replicate them in meaningful numbers. The Americans were producing millions of fuses per year in factories spread across the United States, safely beyond the reach of German bombers. Germany couldn't match that even at the height of their power, let alone in 1945. One German scientist, Dr. Hans Hollmann, who had worked on proximity fuse development for the Luftwaffe, was extensively interrogated after the war. His assessment was brutally honest. We knew the Americans had achieved something extraordinary, he told his interrogators. Even without understanding how it worked, we knew it was changing the war. Our anti-aircraft defences were becoming obsolete, our artillery was outmatched, but there was nothing we could do. We lacked the resources, the time, and ultimately the knowledge to respond. By the time we captured examples and began to understand the technology, the war was already lost. The fuses simply accelerated the inevitable. Hollmann's assessment was supported by broader analysis of German military capability in the war's final year. Even without proximity fuses, Germany was losing. The Wehrmacht was outnumbered, outproduced, and running out of fuel, ammunition, and men. But the proximity fuse accelerated the defeat and made it more complete. German units that might have held out longer surrendered faster. Aircraft that might have gotten through were shot down. Artillery that might have been effective was suppressed or destroyed. The weapon's full strategic impact becomes clear when examining specific campaigns. During the Battle of the Bulge, German forces achieved initial surprise and made significant gains. American units fell back, sometimes in disorder. The offensive threatened to split Allied forces and possibly recapture Antwerp. But within days, American artillery began employing proximity fuses in large quantities. German infantry attacks that relied on traditional assault tactics, concentrating troops for maximum impact, ran into walls of airbursts. The attacks stalled. German commanders couldn't understand why their tried-and-tested tactics were failing. Prisoner interrogations after the battle revealed that many German soldiers believed the Americans had developed some kind of superweapon. They described shells that exploded without hitting anything, creating inescapable kill zones. Some German units reported that American artillery seemed to know exactly where they were and could drop airbursts with pinpoint accuracy. In reality, American artillery was simply using proximity fuses, which made accuracy less critical. A shell that exploded 30 feet above a target was nearly as effective as one that exploded directly on it. The Battle of the Bulge marked the turning point. German forces never again mounted a major offensive in the West. They lacked the strength, but they also lacked the will. Units that had experienced proximity-fused artillery were reluctant to mass for attacks. The weapon had broken something fundamental in German tactical doctrine. At the Remagen Bridge, the unexpected capture of an intact Rhine crossing gave Americans a crucial advantage. Hitler personally ordered the bridge destroyed at any cost. The Luftwaffe committed its remaining strength to demolishing it. German artillery fired hundreds of shells at it. Nothing worked. American anti-aircraft defences, heavily reinforced with proximity-fused ammunition, shot down every bomber that approached. German artillery attempting to range in on the bridge was quickly located and destroyed by American counter-battery fire, using proximity fuses for maximum effect against gun crews. The bridge remained in American hands long enough to get substantial forces across the Rhine. Even after the bridge collapsed from accumulated damage, it had served its purpose. Multiple American armies were across Germany's last major natural barrier. Proximity fuses had helped keep the bridge operational during the critical period. In the Pacific, the proximity fuse's impact on the kamikaze threat cannot be overstated. Japanese pilots flying suicide missions were already accepting death. Traditional deterrence didn't work. The only way to stop them was to destroy their aircraft before they reached the ships. Proximity fuses made this possible. Without them, the losses at Okinawa would have been catastrophic. Some naval historians have estimated that American ship losses could have been double or triple what they actually were if proximity fuses hadn't been available. Each ship sunk meant hundreds of sailors dead. Each carrier lost meant reduced air support for ground forces. The proximity fuse saved thousands of American lives by destroying Japanese aircraft that conventional anti-aircraft fire would have missed. By the war's end, the proximity fuse had become so integral to American military operations that commanders planned operations assuming its availability. Artillery fire plans specified proximity fuses as the standard ammunition for anti-personnel missions. Anti-aircraft defences were built around proximity-fused weapons as the primary kill mechanism. The weapon had gone from experimental to indispensable in less than 3 years. The production numbers tell the story of American industrial mobilization. From 0 proximity fuses in 1940 to 22 million by 1945, from experimental prototypes to mass production in dozens of factories. From a device so delicate it required assembly under microscopes to a rugged weapon that could survive artillery forces and function reliably in extreme conditions. Each fuse contained 130 individual components, many manufactured to tolerances of thousandths of an inch. Multiply that by 22 million, and you begin to understand the scale of the manufacturing challenge. The workforce that built proximity fuses deserves recognition. At Sylvania's Ipswich facility, the largest production site, thousands of workers, predominantly women, assembled the fuses by hand. They worked under strict security, not knowing what they were building, only that it was important for the war effort. The work was tedious and demanding. The components were tiny. The assembly required perfect precision. Mistakes meant fuses that wouldn't work, which meant ships that might be sunk or soldiers who might die. The women at Ipswich and the other factories knew their work mattered, even if they didn't know exactly what they were building. After the war, when the proximity fuse program was declassified, these workers finally learned what they had accomplished. The devices they had assembled by hand, one after another, thousands per day, had helped win the war. The fuses they built had saved countless lives and helped bring about Allied victory. Many of these workers reported feeling profound pride when they finally understood their contribution. Mary Gransbury, who worked at the Ipswich facility from 1943 to 1945, was interviewed for a historical project in 1995. She described learning after the war what she'd been building. "We knew it was important," she said. "They told us lives depended on our work, but we didn't know how important until after. When I learned that the fuses we built had stopped the kamikazes and helped our boys in Europe, I cried. I was so proud. We were just ordinary women doing our part, but our part mattered. Every fuse we built saved lives. That's something I'll always be proud of." The scientific achievement represented by the proximity fuse was equally remarkable. Section T at Johns Hopkins brought together physicists, engineers, and technicians from across American academia and industry. They solved problems that had stumped scientists in multiple countries for years. How do you build vacuum tubes that can survive 20,000 times the force of gravity? How do you create a radio transmitter and receiver small enough to fit in an artillery shell? How do you design a system that can detect a target, calculate distance, and trigger detonation in fractions of a second? Each of these problems required innovation. Each solution enabled the next challenge. The result was a device that represented the cutting edge of 1940s technology, a genuine marvel of engineering that worked reliably under the most extreme conditions imaginable. Merle Tuve, who led Section T throughout the war, received the President's Certificate of Merit for his work on the proximity fuse. In his acceptance speech, he emphasized that the achievement belonged to the entire team, not any individual. Hundreds of people contributed to this project, Tuve said. Scientists who solved theoretical problems, engineers who turned theory into practice, factory workers who built the fuses, military personnel who tested them in combat and reported results so we could improve the design. This was a team effort in the truest sense. No one person invented the proximity fuse. We all did. Tuve's modesty aside, his leadership was crucial. He drove the project forward when others doubted it could succeed. He secured funding and resources. He recruited the best people and gave them the freedom to innovate. He maintained absolute security while fostering open collaboration within the project. He pushed for rapid development and production even when setbacks occurred. Without Tuve's leadership, the proximity fuse might have remained a laboratory curiosity instead of becoming a war-winning weapon. The proximity fuse program demonstrated what American science and industry could achieve when fully mobilized. The Manhattan Project gets more attention for obvious reasons, but the proximity fuse was equally important to winning the war. It cost more than $1 billion. It involved more than 100 companies and thousands of workers. It required solving problems at the very edge of existing technology, and it worked. The fuses functioned as designed, were produced in massive quantities, and fundamentally changed multiple aspects of warfare. In the decades after World War II, proximity fuse technology continued to evolve. Vacuum tubes were replaced by transistors, then by integrated circuits. Modern proximity fuses use microprocessors and can be programmed for specific detonation parameters. They can distinguish between different types of targets. They can be set to detonate at precise distances or after specific flight times. They're more reliable, more capable, and far more sophisticated than the World War II versions. But the fundamental principle remains unchanged. The device senses its environment, detects the presence of a target, calculates the optimal detonation point, and triggers the explosive charge. That principle, proven under combat conditions between 1943 and 1945, remains the basis for modern smart munitions. Today's guided missiles, smart bombs, and advanced artillery shells all descend from the World War II proximity fuse. They're the great-grandchildren of the devices assembled by hand in factories across America 8 decades ago. The proximity fuse also demonstrated the value of civilian scientists working on military problems. Many of the key contributors to Section T had no military experience. They were physicists and engineers from universities and private industry who brought fresh perspectives to weapons development. They weren't constrained by traditional military thinking about what was possible or practical. When military experts said proximity fuses couldn't work, civilian scientists proved them wrong. This model of civilian-military cooperation became standard practice in subsequent conflicts and remains important today. The German failure to develop proximity fuse revealed the limits of technical expertise without adequate resources and institutional support. German scientists were brilliant, but they worked within a system that had decided the technology was impossible. When evidence contradicted that decision, the institution refused to adapt. The 20,000 captured fuse should have triggered an immediate crash program to understand and replicate the technology. Instead, they were examined, misunderstood, and set aside. Institutional inertia and the belief that German engineering was superior to American innovation combined to produce catastrophic blindness. Even when the evidence was literally in their hands, German scientists couldn't see past their preconceptions. This wasn't stupidity. It was the inevitable result of working within a system that discouraged challenging established conclusions, especially when those conclusions came from senior officials and respected experts. If Germany's top scientists had declared proximity fuses impossible, who was going to contradict them? Especially in a totalitarian system where challenging authority could be dangerous. The American system, for all its flaws, allowed and even encouraged challenges to established thinking. When military experts said proximity fuses couldn't work, civilian scientists were free to prove them wrong. When initial designs failed, researchers could try different approaches without fear of punishment. When problems arose, they could be openly discussed and solved collaboratively. This institutional flexibility, combined with vast resources and industrial capacity, made the proximity fuse possible. For German soldiers and aircrew who faced proximity fuse in combat, the experience was often their introduction to the reality of American industrial and technological superiority. Germany had entered the war confident in the superiority of its weapons and tactics. By 1945, that confidence was shattered. The proximity fuse was one of many examples of American weapons that equaled or exceeded anything Germany could produce. German soldiers had mocked American equipment early in the war. By war's end, they feared it. The psychological impact of facing weapons you don't understand cannot be overstated. German troops knew they were facing artillery shells that exploded overhead, but they didn't know how or why. The uncertainty was as demoralizing as the casualties. When you face an enemy with capabilities you can't explain, you begin to question whether you can win. When your own experts examine captured examples of these weapons and still can't understand them, you realize you're facing an opponent with technological advantages you cannot match. That realization breaks morale faster than any amount of propaganda can repair it. In the final months of the war, German troops increasingly surrendered rather than fight. Many factors contributed to this collapse of will, but facing weapons like the proximity fuse certainly played a role. Why die defending a lost cause against an enemy who has weapons you can't counter? The proximity fuse, along with other American technological advantages, convinced many German soldiers that further resistance was futile. The post-war period saw proximity fuse technology spread to other nations. The Soviet Union, through espionage and captured examples, developed their own versions. Britain, which had contributed to early research, refined the technology. France, China, and other nations eventually developed proximity fuse for their weapons. By the 1960s, the technology was widespread, no longer a closely guarded secret, but a standard component of modern weapon systems. The declassification of the proximity fuse program in the 1950s allowed public recognition of the achievement. Articles appeared in scientific journals describing the technical solutions. Books detailed the development history. Documentaries interviewed veterans who had used the weapons in combat. The workers who had built the fuse finally learned what their wartime work had accomplished. The scientists who developed the technology received long-delayed recognition for their contributions. Today, the proximity fuse is recognized as one of the decisive weapons of World War II, ranking alongside radar, the atomic bomb, and other technological breakthroughs that changed the course of the conflict. Its impact on anti-aircraft warfare was immediate and profound, turning a defensive weapon that required thousands of shells per kill into one that could reliably destroy aircraft with hundreds of shots. Its impact on artillery warfare was equally significant, transforming area weapons into precision instruments that could devastate enemy formations. The German failure to develop or even understand the proximity fuse stands as a cautionary tale about the dangers of institutional rigidity and technological complacency. When you decide something is impossible, you blind yourself to evidence that it has been achieved. When you assume your technology is superior, you fail to recognize when adversaries have surpassed you. When you lack the flexibility to adapt to new realities, you condemn yourself to defeat. German artillery crews who mocked the idea of proximity fuses discovered this truth the hard way. Their guns didn't go silent because they were destroyed, though many were. They went silent because proximity-fused counter-battery fire made German artillery positions untenable. They went silent because crews who survived one barrage refused to man their guns through another. They went silent because by the spring of 1945, Germany had run out of trained gunners, ammunition, and the will to continue fighting a war they knew was lost. The laughter that greeted early rumours of American supershells died with the men who laughed. In its place came the terrible knowledge that the enemy possessed weapons Germany could neither match nor counter. weapons that represented industrial capacity and scientific innovation on a scale Germany had never imagined possible. The thunder of proximity-fused airbursts became the sound of inevitable defeat, and German guns fell silent across Europe as the Allied advance rolled on to victory.